Hello. Today we're going to be learning how exponential functions work. We should start with the basics. What exactly is a function? How does it work? Well, a function is a machine that takes in one value and gives us an output of another value. Multiple numerical inputs can give us the same output, but one input can't give us more than one output. If we put in one number, we're only going to get one number back. Okay, that's great. But how do we actually express a function in mathematical terms? For that, we're going to use something called function notation. It starts with the name of the function, usually described by a single letter, commonly f, but also g, h, or even something like q. In this case, we'll just use f for the sake of simplicity. The name of the function is followed by the variable we're using in the equation, bracketed by a pair of parentheses. Then, on the right side of the equation is a variable expression, something like 3x plus 2. We should notice that the same variable, in this case x, is showing up on both sides of the equation. In other words, this equation tells us how to find the value of function f in terms of our variable x. Let's take a look at some sample functions. F of x equals 7x plus 12, g of x equals x over 3 minus 4, and h of x equals x cubed minus x are all perfectly valid functions. Let's take a closer look at each of these functions. Our first function is telling us that to find f of x, we need to multiply x by 7 and then add 12. For example, if x equals 4, f of x is equal to 7 times 4 plus 12, which is 28 plus 12 or 40. Our second function tells us that to find g of x, we need to divide x by 3 and then subtract 4. For example, when x equals 9, g of x, or g of 9, will be equal to 9/3 minus 4, which is 3 minus 4, or negative 1. Our third function tells us how to calculate h of x. We simply take the cube of x, which is x times itself 3 times, and then subtract x from that result. For example, when x equals 3, h of x is h of 3, which is 3 cubed minus 3, or 27 minus 3, which is 24. Now that we've got a general idea how functions work, we can take a closer look at exponential functions. We already know that linear functions give us a simple line, and quadratic functions give us a U-shape or parabola. What about exponential functions? Well, exponential functions give us a curve that increases exponentially, either traveling to the right or to the left. An exponential function follows the general form f of x equals a times b of x plus c. The first component, a, represents our starting value. A doesn't always represent the y-intercept of the function, because it's sometimes modified by vertical shift. Because it's multiplied by our variable term, a also affects the rate of change of the function. However, it's not nearly as important as b, the ratio of change. Every time x increases by 1, the value of the function will be multiplied by b, which explains why the function increases so rapidly. The direction of this increase depends on the value of b. If b is greater than 1, then the function increases as we move to the right. However, if b is less than 1, the function will instead decrease as we move to the right. Finally, c represents the vertical shift of a function. As you might have guessed, vertical shift causes the graph to shift vertically. This is very rare on the actual test. You probably won't encounter it at all. Vertical shift represents a value that's only added once. It's not affected by the exponential increase. So if you see anything in an exponential problem that talks about a one-time fee, that might represent vertical shift. Now let's talk about how to interpret exponential situations. In other words, how do we identify and solve a word problem that requires us to use an exponential function? Let's take a look at the following example. Dr. Thaler is studying a fungus colony. She finds that the number of fungal cells doubles every week. If there were 4,000 cells in the colony when her study began, what function represents the number of cells in the colony, or n, based on the number of weeks that have passed, or t? The first thing we should notice here is the fact that the number of fungal cells doubles every week. In other words, we're being given a specific ratio of change, which means we're working with an exponential function. Let's start by using the general form of an exponential function and plug in values as we find them. First, we need to figure out what variables we're using. In this case, our input is the number of weeks represented by the variable t, and our output is the number of fungus cells in the colony represented by the variable n. Therefore, we want to modify our equation to give us a value for n in terms of t. So n equals a times b to the t power plus c. Now we need to figure out what specific numbers are provided. The question tells us that there were 4,000 cells when Dr. Thaller's study began. This represents a starting value, which means we should plug it in place of a. Therefore, we know that n equals 4,000 times b to the t plus c. We also see that the number of fungal cells doubles, or is multiplied by 2 every week. This is our ratio of change, which takes the place of b in the general equation. Therefore, our equation becomes n equals 4,000 times 2 to the t plus c. What do we do about c? Well, if we look at the original question, we see that there isn't a third number to work with. Like we said earlier, c doesn't usually show up on the test, and it doesn't show up in this problem either. Therefore, our final equation is n equals 4,000 times 2 to the t plus 0, or simply n equals 4,000 times 2 to the t. Another common application of exponential functions is the concept of compound interest. Compound interest is interest that's based on a percentage of the current amount in an account or loan. In other words, it increases by a ratio rather than a constant number, which means we need to use an exponential function. To calculate compound interest, we need to use the following equation, which is a specific variation of the equation we saw earlier. A equals p times 1 plus r over n times 100 to the nt. Okay, that's a monster of an equation. Let's take it one at a time so we can understand what on earth it means. First, A. A represents the current value of the account. Usually, that's what we'll be solving for, which is why it's by itself on the left side of the equation. Next, P represents the original value of the account. In other words, how much are we starting with? Next, P represents the original value of the account. In other words, how much money are we starting with? The variable R represents the annual interest on the account. We can express this in percent form because we're dividing by 100, which means our final answer will be of the correct size. The variable n, which shows up twice in this equation, represents the number of times per year the interest is compounded. In other words, how often is this actually calculated? Finally, our very last variable, t, represents the number of years that have passed since the account was started. Let's go through a quick recap, since that was a lot of information. In our equation, a represents the current value, p represents the starting value, r represents the annual percent interest, n tells us the times compounded per year, and t tells us how many years have passed. For example, let's take a look at the following problem. Saya has taken out a $5,000 loan with a 3.5% interest rate. It's compounded twice a year. If she doesn't pay off any of the loan, how much money will she owe in 5 years? Let's go back to our earlier recap and plug in each of our values. Our current value, a, is unknown. It's what we're trying to solve for here. Our original value is $5,000, so we should plug in 5,000 in place of p. Our annual interest is 3.5%, so we should replace r with 3.5. We know that the interest is compounded twice a year, so we should replace each of the n's in our equation with 2. Finally, we know that it's been 5 years since Saya took out the loan, so we need to replace t with 5. Now that we've got all of these numbers, we can take the equation and solve it, which just means we need to simplify all of the complicated math. First, let's do our multiplication. 2 times 5 is 10, and 2 times 100 is 200. Then we can calculate that 1 plus 3.5 over 200 can also be represented as 1.0175. 1.0175 to the 10th power, simplifies to 1.1894. And 1.1894 times 5,000 is equal to $5,947.22, so that's our final answer. Okay, we've figured out how to process exponents when they're given to us in the form of a word problem. But what about tables? How do we identify exponential relationships in a table of values? Can we even do this? Is this possible? Yes. In fact, it's pretty simple. We know that an exponential function gives us a constant ratio of change when we pass between consecutive outputs. In other words, the ratio is constant when our input changes at a constant rate. Let's take a look at the following table. How do we figure out if this table represents an exponential function? Well, our first step should be figuring out whether the inputs are changing at a constant rate, which we can do by checking the difference. Here we see that each input subtracted from the previous input gives us a difference of 1. Step 2 is the more important step, dividing each output by the previous output, which allows us to calculate our ratio of change. For this particular table, dividing each output by the previous output gives us a constant ratio of change, 5, which means we are dealing with an exponential function. What if we want to calculate an equation based on a table? To make an equation, we need 3 different values. The constant a is represented by the y value when x is equal to 0, in this case 50. The constant b is the constant ratio that we just found, in this case 5. And c is usually absent, just like it is elsewhere on the test. Therefore, our equation in this particular case is f of x equals 50 times 5 to the xth power. If we have the time, it's usually a good idea to plug in values from the table to double check whether or not this equation works. In this case, f of 1 is equal to 50 times 5 to the first power, which can be expressed as 50 times 5, or 250. That's exactly what the table tells us. F of 3 gives us 50 times 5 to the third, which is 50 times 125, or 6,250. Once again, this matches both of the values we see in the table, which means it's probably the right equation. Finally, how do we interpret exponential graphs? An exponential graph can represent one of two things. When b, our ratio of change, is greater than 1, it represents exponential growth. In other words, it will give us a curve that increases as x increases. Remember, this is only true when b is greater than 1. Let's take a look at a specific example and plug in some values to see why this works. In this equation, each time x increases by 1, our y value doubles because our ratio of change is equal to 2. On the other hand, an exponential function represents decay, or a decrease in value, whenever our ratio of change is less than 1. In other words, it gives us a curve that decreases as x increases. Once again, let's take a look at a specific example and plug in some values. In this case, we see that every time x increases by 1, our y value is divided by 2, because our ratio of change here is 1/2. Every exponential function we're dealing with shares one other common trait. It passes through the point 0, a. In other words, when x equals 0, the y value of the function will be a, our starting point. This point will be shifted vertically if we are dealing with a c value in our equation. Instead of being at 0, a, the point will be at 0, a plus c. Let's summarize what we just learned. An exponential function represents a change that occurs at a constant ratio. Exponential functions take the general form f of x equals a times b to the xth power plus c. But c, vertical shift, almost never shows up on the test. When we're dealing with a word problem that represents an exponential situation, we need to find two different things: our starting point, a, and our ratio of change, b. An exponential table has a constant ratio between consecutive outputs. A table representing an exponential function will have a constant ratio of change between consecutive outputs. Finally, an exponential graph is a curve with an increasing rate of change. It represents exponential increase when b is greater than 0, and exponential decay when b is less than 0. Now that we know these techniques, we should be able to tackle just about any question involving an exponential function on the test. If you want to find out more or get in some practice before the quiz, the text lesson is a great place to go for more information. Thanks again for listening, and good luck on the quiz.